if there is not homework posted, I will be sure there is a homework posted by the end of the day. Okay, so. All right. So what we need to do today is we need to go back and summarize this concept of rejection sampling, and then I really want to spend half of the lecture on important sampling as well, so that way you have something to work on in the homework and plan ahead. All right. So rejection sampling, the way I present it, right, is not something you're actually going to use in your research, okay? But it is important to cover it because it introduces concepts that are fundamental to many more important methods. In other words, if we don't cover it, then you'll be wondering what is that and what is this, and from where is it coming? Well, lots of ideas are coming from here. Okay, so we assume that we want to sample from P of X, and we only know P up to some normalization constant. And the idea is we will not sample directly from P, but we're going to sample from some so-called proposal distribution, okay? So the idea here is that this proposal distribution will be way easier to sample, all right? And so you can think if pi is computer code, right, some very complicated distribution, Q can be a Gaussian. Okay, but to be able to use this, we need to have this assumption, and an easy way to remember what this thing is that Q needs to dominate pi of X. So if you think of a unidirectional, a univariate distribution, Q is basically on the top of pi. So this constant M, sometimes you won't be able to find it exactly, but the idea is if you can bound this ratio pi star over Q star by some constant M, then you're fine. Now, what you need to remember that this is an essential constraint. In regions where pi is positive, Q has to be positive. Right? As we said last time, don't expect to be able to search the whole domain of pi of X if Q is 0 there. Okay, so if pi of X is greater than 0, the same has to be true with Q. All right, the algorithm looks like that. Literally, it's a very simple algorithm, 3 lines, okay? So what we do is we sample y from Q of y, and we sample also u from the uniform distribution from 0 to 1, and we accept y with this probability, which effectively means if u is less than that, right? That's how you implement this. That's why you need u from the uniform distribution. So if u is less than that, you accept y, otherwise you reject and you repeat. Okay? So the algorithm basically has this new element here that you sample from the proposal distribution. It has this important step here that says, no, you don't accept every sample because the samples, they don't come from pi, they come from Q. You only accept those samples for which this equation, this constraint is satisfied. Okay? So obviously, many samples are wasted. Okay? But if you think about, if you sample this, if you take the samples from Q of y and Q of y is a Gaussian, it's very cheap to do. So wasting a few things from a Gaussian is not a big deal. Okay? If those samples were coming directly from pi and you reject them, and evaluating even pi is expensive, then you have an issue. Okay? So that's the algorithm. And I highlighted very fast the proof, and I told you in the notes I put 2 different proofs. So what I'm going to do is I am going to use part of the proof we did on last Friday, and then I will repeat the proof with different notation today. So this is, by the way, schematically the algorithm, right? So you pick up a y, okay? This point here is pi star of y. This point here is m prime q star of y, evaluate that y. So that's this m prime times this proposal distribution that dominates pi, okay? And so you evaluate m prime q star at y times u, where u is from 0 to 1, And if it happens that this number it's below pi star of y, so if you're on this heavy gray area, you accept. If you're up there, you reject. So just visually. Okay? All right. And again, you mentioned that this distribution dominates pi. And more importantly, you notice the tails of the distribution have to be heavier. Actually, there are lots of examples in the literature where you try to use this method and you think the tails are almost the same, but if they're not heavier, basically you will get the wrong answers. They need to dominate even on the tails. All right. So in the algorithm, actually, the step that I will use from what we did on Friday is that the probability of acceptance of given here is basically the normalization factor of pi. Okay. Does it say what? So the normalization factor of pi is basically the integral of pi star y dy divided by m prime times the normalization factor of q. So I remind you that when you see star, it's the unnormalizing part of the distribution. Okay, so let's very rapidly do this proof, the probability of acceptance. Notice that when I write the probability of acceptance, there's no mention of any sample here, so you have to use the divide and conquer sum and product rules of probability. So condition this on y, assuming that y comes from q of y. So this, if you draw y, this is the probability of accepting that y, and that's the probability that you see here, right? From where is that probability coming? Because I gave you the algorithm, and now I'm going to try to prove that the algorithm works, right? So this is the probability of acceptance, and I write q of y as q star divided by the normalization factor of q star. So this and this cancels, this and that will give you z, you have m prime, and then you have this, okay? So the probability of acceptance, remember, is the ratio of two normalization factors, and on the denominator you have m prime. So let me give you an alternative notation on the proof why this now algorithm works. So it's basically identical to what I had before, but the notation looks slightly different. So what I'm going to prove is that given that y is accepted, that the probability of y being less or equal to little x is actually the probability of capital X being less or equal to little x. So this is the CDF basically of pi, corresponding to pi, right? So we want to prove that if we accept y, then this probability is actually equal to this. So effectively that the y sample is the sample coming from the distribution of pi of x, which is on the right hand side. All right, so right now you see there are two statements here, that y less or equal to little x, some given value, and y accepted. So you can think of this as a probability on this continuous variable and some sort of a discrete value that says if y is accepted or not. And this is what this integral is about, okay? So I'm again using the divide and conquer, if you like, rules of probability. So y comes from q of y times 1. 1 corresponds to where? Look at that equation and tell me what is that one that I put explicitly. What is that one? You notice here I put this indicator function. It says indicator of u less or equal to this, which is the acceptance probability, right? If u is less than that, I accept, right? What type of variable u is? Uniform. There is the probability of the uniform random variable, okay? So basically, what this says, y accept is this, okay? And y less or equal to x means integration from minus infinity to x. And the distribution for y is q of y, and for u is 1. And then I integrate dy du. Now I can get rid of the integration in u. And will you agree with me if you integrate from 0 to 1 this indicator function in u, that you will get this? It's a uniform random variable, right, equal to 1. So what is the integral of the indicator function that u is less or equal to that? It just adds value. Bless you. You see that? Right? When you integrate on u is, there is nothing, all the other arguments don't depend on u, and this is 0 if u is greater than that, so you basically you get this value, right? So we have pi star q of y dy divided by m prime q star. So let me simplify a little bit. Okay, so tell me, what am I doing here? I can write q. What is q over q star? Q over q star is the normalization factor of q star. All right? So, and because it's a constant, I move it out of the integral, m prime out of the integral, so on the numerator I have pi star from minus infinity to x. All right, done now, because in the previous slide we said that the probability of acceptance is given by this nice ratio, so I can use now the product rule and write this left-hand side. The probability of y less or equal to x, given that y is accepted, is the joint probability of y being less or equal to x and y accepted, which is this, all right, divided by the probability of acceptance, which is that. This thing cancels and this cancels. And then what I get m prime and m star, m prime cancel. And then I have this integral, and I have pi star divided by the normalization factor of pi star, which will give me pi of y, and that's the CDF of pi. Do you see that? This divided by this integral, right, is the CDF of pi. Okay? So effectively, the samples that we get from the algorithm and we accept are really samples coming from the distribution pi. Okay? All right. I mean, you may say, you know, do you actually set the algorithm and then you prove that it works? Well, you know, if you are a genius, you can do it this way or go the other way around. Okay? But the idea here is something so trivial, but so general. It actually, if you look at this, it doesn't really say what the distribution pi is, can be anything. The restrictions on Q are very broad. It just says, oh, it has to be sort of on the top of the distribution pi in some sense, right? And it's very general, okay? And it works, and there is a proof that it works. And because we love proofs, the proofs are given in these two slides, and that's it. All right. Let me give you one fact here that is very important. You may ask, how many samples do I need to take before I accept a sample? The answer is 1 over the probability of y being accepted. That's basically how many times you need to try to accept one sample. Okay, and if you want to say this mathematically, to accept at the kth trial means you have to reject at k minus 1 trials. So gamma here I put the notation to be the probability of acceptance. So I reject k minus 1 and then I accept the kth time. And it comes out, right, this, when you look at this, it's a geometric distribution. And the mean of the geometric distribution, so the kth time where you will accept, the mean is 1 over gamma. So it's 1 over the probability of acceptance. Okay? So geometric distribution, the mean is basically 1 over the probability of y being accepted. Okay? So let me do some trivial examples. We want to sample here from the beta distribution. So what I'm going to do is I am going to use an importance sampling distribution Q, that's the uniform distribution, all right? And because I want this to be on the top of Q, you remember it has to be as close as possible to the distribution pi, because if m is very large, the acceptance ratio will be very low. I mean, you can take it to infinity and say, I'm going to do business, but it's not going to work because all the samples will be rejected. So you want basically to compute the SEM, but this uniform distribution is exactly on the mode basically of the beta distribution. So you can actually take the beta distribution, calculate the maximum with respect to x, all right? And you know, calculate so find the x square maximizes and set this value equal to m. All right, so this value comes to be 48 divided by 27. There's no magic there. Okay, if you take beta distribution and it's beta 3, parameters alpha equal 3 and beta equal to 2, so this m comes to be 48, and so mq is like that. This is the actual distribution, and all of these things are, you see, is a histogram following this accept-reject algorithm, where all the samples are generated from the uniform distribution, about. All right? So what you see here are the samples that are being accepted. Okay? And if you want to see the Monte Carlo, the Monte Carlo approximation of the beta distribution, these are your delta functions that we were discussing in an earlier lecture. All right, here's another example. Let's say somebody gives you this weird distribution and says, find me, samples from this distribution. Okay, so it has e to the minus x squared over 2 that looks like a Gaussian, but it has sine squared and 3 times cosine squared times sine squared plus 1. Okay, so what I'm going to do is I'm going to take, I am going to take as a distribution e to the minus x squared over 2, which is actually a standard normal. Okay, but to do that, I'm going to have to find the constant m so that this thing, it is true. And it's easy to find this constant because you notice the sine is less than 1, right? The cosine and the sine are less than 1, so you have 1 plus 3 plus 1, 5. So the constant is 5, all right? So this is my m prime times q, all right? All right, it's on the top of this pi distribution, and these dots are basically the values of u times plus m prime times q star of x. So basically this gives you all the locations, all the samples that eventually you accepted. So if you do a histogram of this, no bad again. So the accept-reject distribution wouldn't work for something that looks weird. It doesn't have to be a nice smooth distribution. You can do this nicely. All right, so let me give you some more challenging problems. And again, some of these were homework problems, I think, possibly last year. The TAs don't want to give you these problems because they couldn't solve them last year. So they said, let's be nice. So they're still looking for problems to give you that you feel good about. Okay? So the idea is, can we actually use the accept-reject algorithm to sample from the gamma distribution? Okay, so here's the gamma distribution with parameters alpha and lambda. And, okay, so I'm going to actually go fast through this, way of addressing this problem, and then I will actually do it a little bit a more rigorous way. So the idea here is, all right. So the idea here is we are going to sample. So this is actually the distribution gamma, all right, and we're going to sample from this distribution. This is m prime times q, where q is given by this gamma distribution that you see here. Has parameter, so we are basically playing with two gamma distributions here, okay? So this is certainly on the top of the blue distribution. This is the integer part basically of this coefficient alpha. This parameter here is lambda minus 1, okay? And it comes, if you do the calculation, you take the ratio of pi over q, it comes that the coefficient m is the ratio of two gamma distributions evaluated at the point alpha minus k. K is this integer part of alpha, and with these parameters, and then another gamma distribution evaluated at alpha minus k with these two parameters, where again k is that integer part that you see there. Now you may say, why, this looks idiotic, why are you going to sample from another gamma distribution if your goal is to sample this gamma distribution? Well, it's actually not as trivial as that. For this gamma distribution, this alpha can be any number. for the gamma distribution that I use here, this alpha, or I denote here as k, is an integer. And for an integer, we can use the transformations, the equations that we discussed on Friday. And I remind you, if you take n k samples from the exponential distribution, then the sum of the samples, it's actually a sample from a gamma distribution where this k is an integer. So effectively, you can take samples of the exponential distribution, sum them up, all right, and immediately will give you samples for this gamma distribution, and then you can use this as a proposal distribution to work on this problem. But notice again, that's a huge difference, all right? I mean, the two distributions seems to be very close there, but somehow this is way too wide, you know. So this is not necessarily the best approximation, and I think it works, and there is a little computer program that you can see, all right, and it works. So let me give you the real thing on how you're going to sample from a gamma distribution for any alpha. And on the next slide, there is a summary of the algorithm. So this is the gamma distribution, and I denote here as this thing as a function, as a distribution f of x, okay? And I take, just for simplicity, the parameter lambda to be equal to 1. So I am going to use as a proposal distribution a Cauchy distribution. A Cauchy distribution looks like this, okay? And a Cauchy distribution is very easy to sample from, because we're going to need to sample from this proposal distribution. And why the Cauchy distribution is easy to sample? Because the CDF is written analytically like this. All right? You remember an easy way, if you know the CDF and the inverse CDF, how do you sample? You take a uniform sample from 0 to 1, and then you invert the CDF. So effectively, you are going to sample, let's say, call this u from 0 to 1, and then solve for x, and that x is this, where this would be a sample from the uniform distribution. Okay, but now the difficult task, and it took me actually lots of search on the web to actually, you know, somewhere I showed that this was being used, but I couldn't understand why it works. All right? To make it to work, you're going to have to actually show that this distribution, the pi distribution that here I denote as f, has to be less or equal some constant times the Cauchy distribution. Well, I found a paper, 1974. It was, somebody had scanned it nicely and put it on his website and allocated. So you can actually show a nice inequality, and the proof is there, that this pi distribution is less or equal to a constant that you see here, times the Cauchy distribution h of x for these parameters that you see here. Okay? So basically we're in business. Because we can sample from the proposal distribution, we have established what that constant m is, and here is the algorithm, really 4 steps, and I will strongly suggest that you actually read this algorithm, right, to convince yourselves that it's really the accept-reject algorithm, because, you know, you need obviously to be able to do this sampling from the Cauchy distribution, and then you need to have a calculation of accept or reject. So you need to introduce the probability. So, you know, so on this step here is the sample from the Cauchy, okay? And here is basically the acceptance or not, and that's the algorithm. And look how nice this proposal distribution looks versus what I had before. So this is the Cauchy distribution times this constant k, really nice wider tails, right? Heavy tails. This is the gamma distribution for any coefficient alpha. That's the way to do it. And so when you guys run it, you'll be happy that you know how to sample from the gamma distribution. All right. So I'm going to jump a little bit on the slides. Okay, so let me, I am not going to do this example, it's trivial, it's an example. The conclusion is really what I need. you to pay attention here, that the example demonstrates basically that you don't really need to know the normalization constant of Q, okay? So if the proposal distribution, the point is here, is only known up to normalization constant, this is good enough. And in this case, I wanted to sample from a distribution pi that looks like that, and the proposal distribution is either a normalized Gaussian or an unnormalized Gaussian, and basically what you get is that the acceptance ratio and everything else is the same. So you don't really need to know the normalization constant in Q. That's the message here. Let me tell you something on how this accept to reject will work for Bayesian problems. So let's say you're really interested to explore and take samples from the posterior. So the posterior is the prior pi of theta times the likelihood. So the anormalized posterior is this, likelihood times the prior. The obvious thing to do is to take as proposal distribution the prior, okay? And if you think about it, right, that makes sense because the prior is because before you have seen any data, so it's a very broad distribution. The posterior, as you collect data, becomes narrower and narrower, okay? So really the prior is on the top of the posterior, okay? So if you take the prior, okay, and assume here the prior is normalized, so if we need to show that the ratio, you remember, of pi star divided by q star is bounded. So if you take this ratio divided by pi, you get the likelihood, and you want to find the maximum of the likelihood. And guess what? That maximum is really the likelihood calculated at the MLE estimate. Right? What's the MLE estimate? It's the value of the parameter that maximizes the likelihood. So if you compute the MLE estimate, that constant m for the accept reject algorithm is really the evaluation of the likelihood at the MLE estimate. Very nice. Okay? And this is, so if you calculate the accept ratio, it's basically the normalization factor. Surprise, surprise, it comes again here, that we have from the Bayes rule, divided by the value of the likelihood computed at the MLE. All right, so let me convince you now why accept-reject algorithms are bad for you. So I'm going to take a trivial distribution, which is a multivariate Gaussian, and this is in d dimensions, mean 0, right, and variance, identity, and in d dimensions. And the obvious proposal distribution is another Gaussian. I'm not going to, again, go from one Gaussian to another because that's practical. I want to show you why the method has issues. So I'm going to take a proposal distribution, another Gaussian, that has a variance sigma squared I, where sigma is greater than 1. Will you agree with me that if I take the ratio of the two, because sigma is greater than 1, it will be on the top, right? Okay, so I want to see what that will give me for this particular case in d dimensions. So I'm going to take the ratio pi star over q star, and you can show that this is less than 1, that exponential. So really this is bounded by sigma to the power d, right? That's our constant m, okay? Straightforward, there's nothing there, right? Everything cancels out and you get sigma to the power d, and this called two exponentials combined give you less than 1. So the constant is sigma to the power d. So the acceptance ratio is the normalization factor of this distribution, which is actually already normalized, is 1, divided by the normalization factor of q, which already normalized, 1, and m, which is sigma to the power d, but sigma is greater than 1, so as d goes to infinity, this goes to 0. So basically you never accept any sum. So the higher the dimension, the less useful the method is, because every sample effectively would be rejected because the acceptance probability is 0. That's an artificial example, but somehow these particular choices of pi and q are used almost in all Monte Carlo methods to verify if something works or not, right? Simply because they are trivial. So be sure you do that too. Okay? All right. All right, so let me discuss very briefly, because you guys can go and read in the notes, and there are some examples about this envelope rejection method. So the idea here is, let's assume that somehow we can bound this normalized distribution pi from above, the way we had it up to now, but also from below, from some proposal distribution QL star. So this is from, L means from below, right? And somewhere here I'm going to put an upper or something, okay? So let's say that we can bound from below with QL star and from above exactly as what we had before. So here is an algorithm that I want you to look at and tell me if you have any problem with it. So basically we sample Y from Q, all right? We sample from the uniform distribution. This is what is new. And tell me that, so this is sort of an intermediate step that you can terminate the algorithm. It says if U is less or equal to this lower bound QL star at Y divided by M star Q star of Y, then return Y. Will you agree with me if this is satisfied, the theory that we discussed before will accept Y? And why is that? Because QL star, isn't it less than pi star of Y? QL star, right, is the lower bound, so it's less than pi star of Y. And you may say, okay, I see this, if this is, you accept Y. If not, you are actually going to go and do the real checking, which is here. Now, why should you put this intermediate step? Can you think on why somehow you go this extra effort and you put the lower bound and you compute this? Give me one reason why this may be useful. It's all in the symbols here, right? I see the denominator is the same. Here I have a pi star and here I have QL star. When will this be useful? Here you have to evaluate this normalized target distribution, which can be a posterior computer code. The idea here is this lower bound may be some easy distribution. So you don't, when you do this, right, and it happens, let's say that you accept, you do this without actually evaluating at Y the actual distribution. So computation can be very efficient, okay? So the idea here is, if you can bound from below as well, and in addition from above, you can insert this intermediate step and have what is called this envelope rejection method. And you may say, how do you bound the distribution from above and below? What is the, how can you do this? I'm going to give you this in a graphical way. This is only works, I suppose, for univariate distributions. So if the I'm going to use it for distributions that have log concave densities, okay? So basically, they look like this line, this curve that you see here. And what I have done here is, the equations are in the notes. I discretized this distribution at a few points, and then I have bounded from below with this, I don't know what color is that, light blue, all right? And this darker line that you see on the top from above, okay? You can visually, without me having to go on details, you can see, right, this is basically you connect the points to get this light blue, that's the lower bound, and the upper bound is basically you notice this segment here is the extension of this line, all right, and this segment here is the extension of that line. So effectively, you select the minimum of this extrapolation of this line and the extrapolation of that line. So in this region, this is the minimum because the other one goes like that. And in this area, this is the minimum because the other thing goes like that. So anyways, the algebra looks like this. So for univariate distributions, you do this for the log of the distribution. So you bound basically the logs from below and above, okay? Using this discretization and this construct that I have there. And then from here, you can actually come up with the bounds on the distribution pi itself, okay? And then you can apply the algorithm that I just described, this envelope reject algorithm for this type of distributions. Again, this may be nice if you have a weird distribution in one dimension, but in higher dimensions, this method is not going to be very practical. Okay, so we don't need this. Okay, so I'm going to jump. I'm almost done with this lecture. And so let me jump to where I can jump directly. So let's see. Okay, so let me at least do one slide of this. I am going to introduce this concept of what's called this Rao-Blackwellization construct, extremely important. Okay, so let's say that our objective, so we have a distribution pi of x, right, and we want to calculate some expectation of some function. Okay, I kept here h of x, right, a notation. Because I think I copied this from the original paper. So let's say we want to calculate this expectation, okay? And somehow, if you do this with Monte Carlo, it will require taking samples from pi, but that's very expensive, right? That's the whole idea of the Monte Carlo, the accept-reject methods that we have seen up to now. So taking samples from pi is very complicated. So here is what this Rao-Blackwellization algorithm, extremely powerful, does. It's this equation here, so I want you to look at it and tell me what's the trick here, because we already have seen this. Don't read anything else, all right? Do me a favor, just look at this equation, okay? So obviously I'm conditioning here on some y, so what's the idea here? I wanted to find the expectation of this function of x, but now I'm writing as the expectation of this, where the inner argument here is conditional on y. We have seen this, right? So so this is a valid argument. I can condition on y when this calculation can be useful. Well, it can be useful if somehow this expectation condition on y, it's very easy to calculate. Right? If conditioning on y, it's very easy to calculate, that's fantastic. And there are thousands of problems where if you condition them on something, somehow, it's like if you have a Gaussian mixture and say, I'm going to condition it on what Gaussian I have in that mixture. If I know this Gaussian, then I can go and sample from that Gaussian. But doing it on the whole mixture is more complicated. So the estimator becomes, you condition this on y, right? And the outer expectation obviously will be an expectation with respect to y, as we have seen it, okay? And so this is what this Rao-Blackwellization algorithm is all about. Effectively what you're going to do is, you're going to do Monte Carlo estimates using basically samples of this inner expectation that either you know it analytically or somehow you can compute it easily. The only thing I'm going to tell you before I show you the Monte Carlo approximation of this is that the variance of this conditional estimator is actually less than the variance of the original estimator. Okay, and that's why this Rao-Blackwellization method is very useful. Now you can see from have given you this identity. You remember again conditioning on some variables v. I can write the variance of u as the expectation of the conditional variance and the variance of the conditional expectation. So this is greater or equal than this variance term. Okay, so you can show that basically you reduce the variance by conditioning on something. Right? If you know something, the variance of the new estimator is less. So here's the algorithm, okay? And I have many things on the slides that you can look about how you can optimize this, etc. So let me put all of this up. So the idea is y comes from some distribution, can be an arbitrary distribution, okay? So we take n samples from the distribution from where y comes. This can be a discrete distribution, for example, right? So we sample n samples of y. We calculate these expectations, these conditional expectations. And right now, think that somehow you can calculate them analytically, okay? That would be extremely rapid type of calculation. And then what you do is, basically you are going to use Monte Carlo for the outer expectation we had. So 1 over n summation over from k to capital N of these expectations. And that's the algorithm. Okay? And this algorithm has less variance than than the original estimate. Okay? So again, I'm not going to elaborate. There is a lot on the notes that somehow are useful information, but I want you to, if you have time, you look at them on your own. So I'm going to leave those slides there. Okay, so let me tell you a very practical way where this conditioning comes to be very handy. And I know I have used this on my own work, in the context of this multi-element sort of methods. So let me describe again. We have the original problem. We want to find the expectation of H, right? That's the hard problem. And we say, taking distribution of pi, it's a little bit more difficult. So what I'm going to do is, I am going to do this integration over different domains where the distribution pi of x is acting, and I am going to sum all the contributions. So think, if x is two-dimensional, right? You partition the domain in little pieces, and I'm going to sum over those pieces. So let me see how we're going to do this. In every piece, the distribution that I'm going to have here, it will be the conditional distribution of pi of x. So look carefully on this thing, what it is, right? So this is, think again on the square. Let's say on this region, I'm going to do one of these calculations, where the distribution is the conditional distribution of pi with the assumption that I am in this domain. All right, that x is in this domain. How do I take care of that? Because I put an indicator function that says, if you're not in that domain, this distribution is 0. All right, so if you take the conditional distribution that you are in the domain M, and you do this by introducing this indicator function, Cm is the normalization factor, the probability that you are in the domain. So obviously, if I am going to put a Zm there, I'm going to have to put a Zm there. So effectively, you can see what it is literally it's the sum and product rules, isn't it? All right, I am saying this will be the probability that I am in domain M, which is this, times this conditional expectation. What's the conditional expectation? Is the integral of H times the conditional PDF, okay? And the integration of the little domain dr. So again, think where you may want to, rather than doing this whole integral over the whole domain, you partition in little domains. In each domain, you actually calculate the conditional PDF in that domain. Okay, this is very useful. You will see it in the literature in very different sort of scenarios. All right. So what did you do? All right. So what you will do is you will calculate with Monte Carlo each of these things separately. All right. So how do you do this? So you will take. So we are trying to calculate. We take samples from this conditional distribution PM. All right. So for each of the domains, we will draw NM samples. All right. So NM samples are the samples drawn from PM at the domain M. All right. So these are the samples, and we approximate this with Monte Carlo. All right. And then the whole estimator. We have summation over all the domains that we partition of these probabilities that work in this domain, and then the Monte Carlo estimates. Okay, very useful sort of calculation. And if you are interested, you can compute the variance. So the variance will be sigma Zm squared times the variance of these local estimators, which you remember is the exact variance divided by the number of Monte Carlo evaluations. And if you do sort of, if z is like an integer variable, if you partition, let's say, the line in m pieces, and the number of points that you take in every piece is the total number of points divided by m, this is sort of a very specific calculation that you see in the literature in calculating the variance of this estimator. Okay? And you can show, again, that the variance of this estimator is actually less than the original variance of the variance of the original estimator. So basically, again, if you condition things on something, the variance is reduced. Okay, so in this case, you get what's called a stratified sampling estimator. Okay. We are slide 69. So what I'm going to do is, now I'm going to change direction because some of you are sleeping, so I need you to get up to speed. All right. So I'm going to switch and discuss an even more important method for doing sampling, which goes with the name important sampling. This is a huge topic, has implications on everything, and it leads to many sort of modern methods for working with dynamical systems and time series. You say it, okay? So this is sort of a very important lecture. I'm going to go directly, actually, so this is sort of a review. We already discussed this in the beginning today. All right. So we're going to keep from the accept-reject methods this idea that sampling from the distribution pi is complicated, it's expensive, cannot do it, so we're going to sample from a proposal distribution. So that idea, we're going to keep it. But we're going to try to do something different from accept-reject methods. We're going to try to generate samples that are drawn from Q in a way that we keep all the samples. We don't reject anything. All right? So we're going to keep all the samples. We're not going to reject any sample. And the only constraint, there's not going to be any bounds or anything like that I had before. Nothing. The only constraint is that in regions where the distribution pi is positive, Q also should be positive. Right? Makes sense. So let's see a trivial calculation, how this method is, because everything that has sort of is universal, it is trivial, all right? It is trivial. It doesn't maybe look trivial when you think about it, but after when you read it, you say, I could have done that, right? So let's see what you could have done in your home. You want to calculate the expectation with respect to pi of f. So that's the definition of the expectation. So what I'm going to do is divide and multiply by q. I can do this because q is positive, okay? And now, immediately, you can see something nice. This, doesn't it look to you like an expectation, but an expectation not with respect to pi, but with respect to q? Can you see that? It's an expectation with respect to q, not of f, but f times pi over q, which is another f, another function. As a matter of fact, I call that function f subscript q. Or I can, if I call this ratio pi over q as w, then my new estimator is really an expectation with respect to q of w times f, where w is the ratio pi over q. So the idea is, if you look at this equation, right, extremely powerful, it says you really want to, obviously, if you don't sample for nothing, right, you want to calculate expectations. You want to calculate an expectation of f with respect to this distribution pi. Well, you know what? It's the same as taking expectations with respect to any distribution Q that satisfies this. But be sure here, you don't take the expectation of f, but w times f. So basically, you correct the fact that your expectations are not with respect to pi, but with respect to q. We're in with that? Makes sense? All right. Of course, we need to figure out, is this practical? Does it make sense? Because everything I tell you, right? I always tell you at the end, oh, this is not very good anymore. But there must be a reason why we need to do this. So, let's pose the algorithm, right? So we're going to take n samples from the distribution Q of x. So you remember the expectation of f with respect to pi is going to become now an expectation with respect to q of f times w, and this is what the result is. You remember my precise notation here? We approximate all the expectations using the Monte Carlo approximations of distributions. So if I take the n samples that result of this distribution q hat subscript n, then basically the approximation that I use is 1 over n summation of the w's times calculated xi times f of xi. Right? So now you see immediately, right, that this looks like a Monte Carlo thing, but the weights now are not anymore the same. So the weights basically are needed to account for the fact that we don't really take samples from the actual distribution, but we take samples from another arbitrary distribution, proposal distribution Q. So these W's basically do this. They are the magic element basically that allow us to do this. So the weights are given pi divided by Q. And right now, the way that I have the whole presentation, I'm assuming everything is normalized, right? But we will see if somehow there's any hope for this methodology to apply to non-normalized distribution. So let me, this is the Monte Carlo approximation of Q. You remember? Right? Our notation has to be rigorous here. The samples of xi are from Q. The weights in the approximation of Q are looking like that. And on the bottom now, you see the Monte Carlo approximation of pi of x, where the samples come from the distribution Q, not from pi. Right? So we have these delta functions that were introduced here, all right? But the weights, right, the weights are accounting for the fact that these are not samples from pi, they're samples from Q. By the way, you say, I don't believe you, why is this correct? Well, you know what? Take this and compute the expectation of that, then you will see that you get that result. So I'm basically doing this calculation here on a reverse, and this is the Monte Carlo estimation of pi, where the samples are coming from another distribution, not from pi, but from Q. This is, I don't know if you have seen this, right? But this is sort of not a tiny little step. This is very significant, right, this equation. We are able to write the sample approximation of a distribution where the samples are coming from another distribution, another arbitrary distribution. Okay? And we can compute any expectations, all right? The only difference is you just have to basically multiply your function f that you want to compute averages with this weights w of x. So let me, I don't know what's happening here. So let me put you some statements, and you can show them actually on the slides. There's really nothing to it. The equations look a little bit different from what we did with the standard Monte Carlo methods because there is the weights there, and there are two distributions, pi and q. So the first thing is the estimator is unbiased, okay? So if you take your estimator and you take expectations with respect to the underlying distribution, you get the exact, basically, expectation of x, of f of x. The variance, right, you remember the variance would be, the problem was transformed to, the estimator was transformed to an expectation with respect to Q of W times F. So the variance from our Monte Carlo calculations from earlier lectures would be the exact variance of W times F with respect to distribution Q divided by N. You remember that? All right? And if you expand it, all right, you may say, wait a second, where did you get this type of thing? Here is an expectation with respect to pi. You know what the first term is supposed to be? Should be an expectation with respect to Q of W squared, F squared times Q in the integral. When you take the variance is the variance of the argument squared minus the expectation squared, right? So the expectation here, you have W squared F squared times Q, because the expectation is with respect to Q. So W squared will give you pi squared over Q squared, the Q squared and the Q will cancel. One of the pi over the Q's will give you W, the other pi will give you the expectation with respect to pi. Just playing with arguments here just to make things look nice, okay? So this is what you get minus that. And for what we require basically is that the variance is finite, and there are more strict requirements. A lot of people basically, they say for this to work is basically you have to enforce that the weights are less than infinity, they're bounded, right? So this is a fundamental thing to worry, or you know, the variance of the weights has to be finite, or you know, here you see the expectation of the weights is finite. I think if you enforce this, you get all the other goodies as well. All right. Can you actually compute the normalization constant of the distribution pi with important sampling? The answer is absolutely yes. If you divide and multiply by Q, then what you have is you have the expectation with respect to Q of pi over Q. So really the normalization factor, this is an amazing result, by the way. Because if you guys are going to do any research and you take samples, you know, and you want to calculate the normalization factor, you'll be surprised. You will see in the literature, people are summing the weights, all right, for the samples divided by 1 over n. They say, that's the normalization factor. And you say, from where is it coming? Well, it comes from a one-line calculation, all right? So if you sum the weights, right, times 1 over n, that gives you the normalization factor of the distribution pi effects. And if you remember, the normalization factor is a difficult thing to compute. So an example, we are trying, there's a function here, no, this little function, what's the color there? What color is that? Purple, whatever? What is it?
Green.
Green, thank you. I believe it's green, okay, I don't know. Okay, so let's say this is green. So what we do, we need to integrate this function f, okay, that has this Gaussian-like looking terms. And so we put on the top of them, we put a proposal distribution that's a mixture of two Gaussians, and you can see them, this blue two Gaussians, okay? So effectively, if you try to do important sampling on this, and you want to calculate the integral of a function, all right? So here we have a function, right? And we want to calculate an integral. And you can, again, when you have integrals, right, you can think of this being an expectation with respect to the uniform distribution, which is 1. If you don't wait for the problem to say, I have expectation. You make it to look like an expectation, so you put a uniform distribution on this on square domain, that's 1. And then you don't sample really from the uniform distribution, you sample from this Gaussian mixture, all right? And the results basically for this integral, you basically get more or less, you know, with like 1,000 samples, you hit the right answer, okay? And so you can calculate integrals like that with stochastic methods. What is new here is, because the proposal distribution is a mixture of two Gaussians, how are you going to sample from a mixture of two Gaussians? What would be your common sense algorithm to sample because we're going to need samples from Q. So how do we sample from a mixture of two Gaussians? I mean, obviously, what you will need first to do is you will need to introduce some discrete value. So you will need to condition this on if you are on this Gaussian or in that Gaussian, and you will make these probabilities of these variables to be on this Gaussian 0.46 and 0.54. Right? So you select what Gaussian you are, and then when you are on that Gaussian, you go and you take samples from this, or you take samples from that. All right? That's how you sample. You have to do conditional on the mixture components, and that would be it. And actually, I see here, there is the algorithm. Here is another very nice example, right? There are two exponential distributions put together. Usually the exponential distribution goes to the right, but it's a double exponential like this. And so we're trying to use a proposal distribution that's a Gaussian and a proposal distribution that's a student t. Now, you look at this double exponentially, I see lots of zeros, right, as it goes asymptotically to 0. But if you try to do this integral with Gaussian, important sampling basically gives you unacceptable answers. Basically, this is, so you remember, this is the distribution we want to sample, right? So in one case, we're going to be sampling through a Gaussian, in my important sampling, the other one through student t. So obviously, you expect when you get the sample representation of this double exponential to get lots of samples in the center and less sample towards the tails. And look what happens. So lots of samples in the tails look wrong. And why they're wrong? Because the Gaussian is less fat than the double exponential. All right? So basically the tails of this double exponential are heavier than the tails of the Gaussian, and basically you are ruined because of that. So visually, they look and say, hey, it's okay. Well, no, it's not okay. All right? And if you do this with student t, look at that. You just get right to the right answer because the student t distribution has heavy tails. All right. You may ask, since the distribution Q is arbitrary, is there any such a thing as an optimal distribution? I mean, we don't know if there is or if it is going to be useful. Is there any distribution that is optimal? So, so let me ask before I give you the answer. I see it there, unfortunately. But if there is an optimal distribution, optimal, what does optimal will mean? I mean, can you give me some idea on what exactly optimal may mean in this case? So we're looking to sample from Q so we can calculate, let's say, some expectation with respect to pi of a function f of x. Optimal will imply what? What do we want for something, in this case, to be called optimal? Say it again?
Last deviation.
Less deviation, you said? So minimize the variance. So we want to minimize the variance of the estimator. All right? So guess what? The Q that minimizes the variance of the estimator is actually the absolute value of f times pi divided by this integral in the domain of pi of the absolute value of f times pi. And that is the optimal distribution that minimizes the variance of the estimator. How do you compute this? The calculation again, you know what? I know I do lots of proofs, etc., because otherwise these things will make no sense. Really what you need to do is take the variance of the estimator, and you remember the variance of the estimator is the variance with respect to Q of W times F, right? Because that's how we transform the problem, all right? And so if you expand, you can show, if you plug in this in there, that basically the variance comes equal to 0. Okay? There is really, it's sort of, it's a one-line calculation, but this is how the answer looks like for this optimal estimation. Now, obviously, This not very practical because it requires that first there is this absolute value of f, so if f changes signs, this can be a problem, and then of course you have to calculate this integral in the denominator that is not practical basically to do, but it's sort of good to know that there is such a thing that minimizes the variance, all right, and that thing is given like that. All right. So we have 10 minutes left, right? And so I have to go back and correct the method because, you know, we mentioned even on these accept and reject methods that we did not know the distributions. We only knew them up to a normalizing factor, okay? So if I don't know pi, but I know pi star, if I don't know q, but I know q star, can I actually apply importance sampling? I mean, this is essential, right? Because when you do Bayesian inference, you don't really know the normalizing factor. The cost of calculating the normalizing factor, it's enormous for a high dimensional problem. So you really know the likelihood times the prior. That's pi star, right? So we don't know complete pi, we know pi star. And let's say similarly, we know only q star. Can we actually apply this idea? So I need to show you an identity before I do this. And it's an identity with playing with trivial notations here. Do you agree with me that pi is pi star divided by the normalizing factor? Yes? All right. So on the numerator, I multiply, divide by q star. Inside the integral denominator, I divide, you know, and multiply with q star. I call this w star. So w star now is the ratio of the anormalized weights times q star. And this is w star times q star the integral. And because, you know, there is q star here and q star, really this is pi is w star times q, integral of w star times q. Okay? I'm going to use this equation shortly. The key thing here is this is the actual distribution, this is the actual proposal distribution, but this w star is the ratio of the anormalized weights. So we go back to our real problem. The real problem is, can we compute the expectation with respect to pi of f of x? That's the real problem. So what have I done from here to there? What have I done from here to there? Take a look. Pi equal w star q divided by this integral. W star q, let me see. W star q divided by this integral. All right? And so let me write nicely the numerator. The numerator then is an expectation with respect to q of w star times f. All right? And the denominator is an expectation with respect to q of w star. And, you know, so you can, if you, you know, play with the algebra, you will see actually this is really equal, again, to the ratio of the expectation with respect to q of w times f and the expectation with respect to q of w, okay? So the estimator now, I want you to give me your thoughts here. If we only know w star, all right, to estimate this expectation, we can only approximate it as what? As the ratio of what? Here I had this expectation, right? Can we do Monte Carlo on the term of the numerator? Can we sample this with sequential Monte Carlo? Can you guys give me a Monte Carlo estimate of the equation on the top? This expectation. Yeah, you take n samples of, from Q, and then you will have 1 over n summation of w star at xi times f at xi, done. And then, what do you have in the denominator? It's another Monte Carlo estimation, should be summation of 1 over n of the summation of the w stars at xi. The idea here is that this estimator has now become the ratio of what? Of two Monte Carlo estimators. This has lots of implications. That's not good, right? But if you don't know W, but you only know W star, all right, the estimator that you want to compute, so we can still do it, but now becomes the ratio of two Monte Carlo estimators, okay? So let me see our notation, okay? So here is, in this case of a normalized, weights, basically this is how the distribution Q looks like. If we take samples from Q, Q is our standard Monte Carlo estimator, but now our estimator for the distribution pi, if we draw n samples from Q, looks like this, where this weights, you remember there was an estimator on the top that I had, an estimator on the bottom. So this new weights, this is little w and this is capital W. So in the Monte Carlo approximation of pi with samples drawn from Q, the weights here are what type of weights? Capital W, little w. What weights are those? You remember to be able to get, right, what I showed you before, okay? If I go back to this equation, it was one Monte Carlo estimator here divided by another Monte Carlo estimator. So the weights that I'm going to be getting will be the weights I get there divided by the sum of all the weights. So what I will get is I will get normalized weights. Can you see that? This will give me summation, right, with Monte Carlo, 1 over n summation of W star at all the xi's. And here I'm going to have summation over i's of W star xi times f at xi. So this term divided by the whole summation will give me normalized weights. So the Monte Carlo approximation of pi, it is looks like this, okay? And the weights that are used here are the normalized weights. So the idea here is very simple. If you have, if pi is only known up to a normalizing constant, you can apply important sampling. The approximator basically will look like this, where the weights are not your wi's that we had before, they are the normalized weights. This is little w, this is capital W, these are the normalized weights, and the approximation of the distribution pi is these delta functions defined by Q, all right, times this normalized weights WR, okay? So the, again, if you look at this estimator carefully, don't be confused, it is the ratio of two estimators. If you plug in this inside there, you will see W star at xi times f at xi, and then in the denominator you will see the summation, which it's another estimate. This has implications, you know what? In questions like, is this unbiased estimate? So if I take the ratio of two Monte Carlo estimates, do you think it's unbiased? In other words, if I take the expectations, this with respect to the true distribution, am I going to get the actual expectation of f? And what the variance is if you have two estimators, the ratio of two Monte Carlo estimators? Well, I am going to give you the answers, okay? The derivation is using what's called the delta method, that you guys, that you love calculus, it's only 2 pages long. All right, so so if you look at so this is our approximation, all right? This is the true expectation, right? This is what we get, and the result, basically, one of the two results I'm going to show you, this is from the central limit theorem. It shows basically that this, I mean, I could have put this inside there, right? But it shows basically that asymptotically, this formulation is unbiased asymptotically, okay? But there is, in this calculation here, you notice there is a variance term that comes, okay? Which is the variance basically with respect to Q of W times F minus the expectation, the true expectation of f. Okay, so asymptotically, the estimator is unbiased. Okay, but you can see here, if you take the bias square, right, it is 1 over n basically variation. The bias square is 1 over n variation. Okay, but asymptotically is unbiased, only asymptotically. Okay, and if you want to okay, so this is what I had before, right? If you take this bias, if you like, this bias basically is 1 over n times this variance term that you see there. Okay, and what is so the bias squared is of the order 1 over n squared. Okay, and the variance of the order 1 over n. And if you want to ask what is the optimal distribution for this normalized important sampling, the calculation looks almost identical to what we had before, but here you have f minus the expectation of f inside the absolute value. Okay, and I'm going too fast now, but so when you do this important samplings, right? I'm going to come back to this, you know, after the break. But when you do this important sampling, if you take, let's say, n samples, the n weighted samples, it comes out that these n weighted samples, they are actually equivalent to m samples with a normal Monte Carlo method. Okay, because somehow these weighted samples, right, they're correlated. So if you take n unweighted samples, the relation between m and n is like that. So effectively it's like taking n samples, but in reality the equivalent number of Monte Carlo samples that you get is way less than n. Okay, because of the this variance that we have in the